Every SOC analyst eventually needs a way to interrogate logs directly, not just watch dashboards, and that's exactly what Kusto Query Language does. It's the read-only query language behind Microsoft Sentinel, Defender XDR, and Azure Monitor, and it separates analysts who merely look at logs from those who actually interrogate them. This tutorial works inside a sandbox cyber range built around a simulated logistics company, Azaki Freight and Logistics, generating over 2.4 million events a day across 7 log tables that behave exactly like production Sentinel and Defender data. Somewhere inside that range is one live breach, and by the end of this course you'll have hunted it down using nothing but KQL. Before writing a single query, it helps to understand what a log actually is: a time-stamped, structured record of one thing that happened on a machine, a logon, a process launch, a file write, a configuration change. Individually each entry looks mundane. A logon succeeds. A process starts. A file gets written. A firewall rule changes. But strung together in sequence, they tell a story, and in this case the story ends with an alert, an inbound RDP connection from an unrecognized geography, originating from an address in Romania. Every log entry an analyst works with breaks down into the same 4 parts: a timestamp that anchors it in time, a source or host that identifies where it came from, an action describing what happened, and a set of structured fields: account names, process IDs, IP addresses that become the columns you filter and query against. Every log generated in an environment like this lands in a log analytics workspace, where it's organized into tables by data source rather than dumped into one undifferentiated stream. This particular workspace holds 7, security event for Windows security events, device process events for process creation with full command lines, device network events for connections in and out of each device, device file events for file activity, device registry events for registry changes, syslog for Linux and network appliances, and device logon events, the one that matters first, since it's where interactive, RDP, and network logons are recorded, both successful and failed. Each table carries its own schema. Device logon events, for instance, exposes a timestamp, device name, account name, and action type as its core fields, along with remote IP for tracing where a logon actually came from. With the workspace mapped out, the only thing left is to ask it a question. Every hunt starts the same way: bound the time window, then filter down to the behavior that matters. A query against device logon events restricted to the last 24 hours and filtered to failed logon attempts alone returns 38,412 rows, a number far too large to read through, but not too large to keep narrowing. Most of that volume traces back to a single external address, 185.220.101.47, hammering the account names J.Tanaka, admin, and administrator against one host, WinFRT042. A couple of stray failures from unrelated hosts and IPs sit in the mix too, probably unrelated, but worth remembering, since threat hunting rarely wraps up as cleanly as it starts. 38,000 failed logons is still noise, not evidence. Adding one more constraint restricting the query to the specific source IP that stood out, 185.220.101.47, collapses that number from 38,412 down to just 4. All 4 failures land within a 21-second window, each one testing a different account name against the same host. A single IP address burning through several account names in a matter of seconds is a textbook signature of an automated brute force attempt, not a person who forgot their password. Reading rows one at a time only goes so far. At some point the question shifts from what happened to what's the shape of what happened, and that's exactly what aggregation is for. Grouping the failed logons by source IP and target account and counting them reveals that one address, 185.220.101.47, is responsible for 61 of 65 total attempts, spread across 4 different account names, with the heaviest pressure on the built-in administrator account. Two other IPs barely register a couple of stray attempts each, almost certainly unrelated. The aggregation makes the brute force pattern impossible to miss: one attacker, one IP, one host, 4 accounts tried in sequence. Result set built for analysis rarely doubles as a result set built for a report. Column names like remote IP and account name make sense to a query engine, but a ticket reads better with plain labels like attacker and target account. Renaming and trimming down to just the columns that matter, while filtering any IP with 5 or fewer attempts, leaves 3 clean rows, 1 confirmed attacker, 3 targeted accounts, ranked by how hard each one was hit. Between bounding the time window, filtering to the signal, aggregating into a shape, and reshaping the output for a human reader, that's the complete core toolkit for operations that cover the vast majority of everyday hunting. It has just landed, and it's time to put that toolkit to work on something real. The case, Azaki 2291, flagged critical, opened automatically after anomaly detection caught an off-hours RDP session paired with a geographically impossible logon. The scope is WinFRT 042, the contracts file server at Azaki Freight and Logistics, the same host that turned up repeatedly during the brute force analysis a moment ago. The objective is broad by design: determine how the attacker got in, reconstruct their full timeline on the host, and establish whether they achieved persistence, command and control, or data loss. There's already one lead worth chasing: that RDP brute force pattern uncovered a moment ago. Brute force attempts against WinFRT 042 all failed, but that doesn't mean the attacker gave up. Pivoting from failed logons to successful ones from that same source IP, within the hour surrounding the brute force burst, returns exactly 1 row, at 9 hours 23 minutes and 2 seconds, the built-in administrator account logged onto WinFRT 042 remotely, logon type 10, remote interactive, meaning RDP, from 185.220.101.47. One of those brute force attempts landed. That single successful logon is the confirmed initial access point, a brute-forced RDP session against a local administrator account, mapping to 2 MITRE ATT&CK techniques: T1110, brute force, and T1078, valid accounts. Attackers rarely bring in tools that live cleanly on a system. They stage them somewhere that doesn't draw attention, and a world-writable folder like public is a common choice precisely because any account can write there without triggering a permissions error. Querying file creation events on WinFRT 042 in the minutes right after that successful logon turns up 2 files dropped into the public folder, an executable named svgost_update.exe, styled to look like a routine Windows update component, and a companion file named stage.tmp. Both appeared within seconds of the administrator logon, automated, not manually typed. Naming a malicious binary after a legitimate system process is a classic masquerading technique, MITRE T1036, paired here with the file transfer itself, T1105. Dropped binary that only runs once is a minor nuisance, one that survives a reboot is a foothold. Checking the registry for changes to the Windows run keys in the minutes following the file drop surfaces exactly one new value, WinUpdate SVC, added under the current user's software run key, pointing directly at that same svgost_update.exe sitting in the public folder. That single registry value is what turns a one-time file drop into standing persistence. Every time this account logs on, Windows will now execute the attacker's binary automatically. It's MITRE technique T1547.001, registry run keys, and it's the clearest possible link tying the staged file back to a deliberate persistence mechanism. Sophisticated attackers rarely rely on a single point of failure, so it's worth widening the hunt across the host to check whether a second, independent foothold exists alongside the registry run key. A search for scheduled task creation on WinFRT 042 turns up exactly that, a task named Microsoft Edge Update Task Core 2, again disguised as legitimate update infrastructure, configured to launch that same svcost_update.exe every time the account logs on. Two separate persistence mechanisms, planted minutes apart, both pointing at the same payload. That redundancy is deliberate. If a defender finds and removes one, the other quietly keeps the foothold alive, which is exactly why hunting for persistence means checking more than one location. A persistent foothold is only useful if it can communicate back to its operator, so the next step is finding out where that staged binary is phoning home. Filtering network connections down to only the ones initiated by svcost_update.exe and grouping them by destination reveals a single external server, 45.83.91.201, contacted on port 8443 over TLS 214 separate connections spread across roughly 4 hours, arriving at an interval close to 60 seconds apart. That kind of regular, low and slow check-in cadence to one external address is the classic signature of command and control beaconing, not ordinary application traffic. MITRE ATT&CK 1.001, communication over a standard web protocol, paired with the use of a non-standard port to blend in, T1571. Beaconing implant checking in every 60 seconds usually means there's an operator actively driving the intrusion, not just an automated payload running unattended. And an active operator on a compromised host with local admin rights almost always goes after credentials next. Searching process activity for anything referencing LSASS, the Windows process that holds credentials in memory, or for known credential dumping tool names, turns up procdump64.exe launched with flags built specifically to dump the LSASS process to disk. That's MITRE ATT&CK 1003.001, LSASS memory dumping, a technique that hands an attacker the material needed to extract every credential cached in memory on this host, and potentially to move well beyond it. A careful attacker doesn't just achieve their objective, they try to erase the trail that would let a defender reconstruct what happened, and Windows conveniently logs exactly one event type that records its own deletion, event ID 1102, generated the moment the security audit log is cleared. Filtering to that single event ID on WinFRT 042 confirms it happened, at 9 hours 34 minutes and 2 seconds, executed by the same administrator account compromised earlier in this timeline. Clearing the log doesn't erase everything. Event ID 1102 itself survives, almost as a fingerprint of the attempt, but it does mean the investigation now has to lean more heavily on EDR telemetry and network logs, since the native Windows audit trail on this host has a deliberate gap. This is MITRE ATT&CK 1070.001, Clear Windows Event Logs, Textbook Anti-Forensics. The contracts server exists for exactly one purpose, to hold contracts. So a large, unusual outbound transfer, especially one timed right after the attacker just cleared the evidence of their own activity, is worth checking immediately. Summarizing outbound traffic by bytes sent since the moment the log was cleared turns up one destination that dwarfs everything else, roughly 312 megabytes push to paste-drop.io in a single connection, a volume that lines up closely with the size of the contract archive the server hosts. That's MITRE T1567, exfiltration to a web service, and the timing is not a coincidence. Clearing the logs and exfiltrating the data back to back is a deliberate sequence. Destroy the evidence, then take what you came for. Before closing out the timeline, it's worth checking one more thing. Did the attacker use those stolen administrator credentials to reach beyond this one server? A search for process activity launched under the compromised administrator account, specifically involving PsExec, a legitimate Windows administration tool frequently abused for lateral movement, turns up a connection from WinFRT 042 to a second host, WinFRT 017, running a simple reconnaissance command to confirm the session's privileges. That single PsExec execution, MITRE T1021.002, lateral movement over SMB and admin shares, means the scope of this incident just grew. What started as a single compromised file server is now, at minimum, a two-host incident, and everything discovered on WinFRT 042 needs to be rechecked against WinFRT 017 as well. A finding that isn't written down didn't happen. Every SOC expects an investigation to close with a clear, evidence-linked report, not just a verdict. This one tells a complete story. A brute-forced RDP session led to full administrative compromise of the contract's server, followed by credential theft, anti-forensic log clearing, roughly 312 megabytes of exfiltrated contract data, and lateral movement to a second host. 11 distinct MITRE ATT&CK techniques chained together from initial access through impact. The recommendations that follow directly from this timeline: disable direct internet-facing RDP, enforce multi-factor authentication on every privileged account, alert on event ID 1102 the moment it fires, and monitor world writable folders like public for new executable writes. That's the complete arc of this course, from what a single log entry is, all the way to a documented, MITRE mapped incident, built one KQL query at a time.